not going to talk about domain-driven design, although I love this methodology, but there is another book that I'm working on for quite some time now, and I want to give you a preview into this book's material, and that's Balancing Coupling in Software Design. System design is inherently about boundaries, what's in, what's out, what spans, what goes between, and it's about trade-offs. It summarizes the topic of this talk. I want to talk about system design, but more specifically, what goes between those boxes. When we design systems, usually we focus on those boxes. Objects, services, whatever. But we tend to pay less attention to lines connecting them. And that's where our worst enemy comes into play. Things we fear the most, coupling. And you know, we've been told that coupling is the enemy of design. It's like when we are working on a system that tends to resist any changes we are trying to make, we are blaming it on coupling, of course, right? So, not surprisingly, what do we want to do about coupling? Well, we want to decouple everything. We want to eliminate coupling completely. However, oops, it's really hard to work with only one display. However, when we tried to take, let's say, a monolithic system and break it into tiny, tiny boxes, and they can be whatever we want. They can be objects, classes, services, microservices. Now it's serverless functions. And if we're focusing only on size, we are going from coupled piles of code, as you've already seen, to decoupled piles of code. And this is not surprising because, for example, as my friend Matthias says here, going for as small as possible is almost universally a bad advice in software design. Also, Nick Tune says there are many useful and revealing heuristics for defining the boundaries of a service. Size is the one of the least useful. And yet, we keep on doing that. So, in the 40 minutes or something that I have left, I'm going to try and define what is coupling. We're going to explore the dimensions in which coupling can manifest itself, and then I want to try to do something crazy. I want to try to convince you that we can use coupling as a heuristic for designing modular systems. So, let's start from the beginning. What is coupling? And if we go to the lexical origins of this word, it will take us all the way back to Latin, where it was composed from co and coopere, meaning fastened together. So in that sense, if two things are coupled, they are simply connected. And that makes coupling a ubiquitous phenomenon. It is everywhere. Like this clicker, it is coupled somehow right now to my computer. Somehow it works. Organs in our bodies are coupled to produce us, living organisms that produce code, or stress hormones in my case right now. Or in any way, any system, whether it's a company, a car, a city, all of them are held together by coupling. Because if we remove those connections, if we remove coupling entirely, and we just leave those independent components without any interactions between them, that's what we'll get, a bag of components, but not a system. We need those connections to make the value of the overarching system to be higher than the sum of its parts. So, trying to completely eliminate coupling can lead to undesirable results. So, instead, let's try to acknowledge that software design is not only about drawing boxes. We have also designed the interactions between the components. And I'm purposefully using abstract terms like components and modules because coupling can take place at all levels of abstraction. It can affect classes, services, whatever. So let's see a little example of how coupling affects the design, and then we're going to explore it in more detail. So let's say we have these two components. we have downstream that references and thus depends on the upstream component. The line between them defines how a change in the upstream component will affect its consumers, its downstream components. The more information is shared by the upstream component, the more likely that changing any of its implementation details are going to produce cascading changes in other parts of the system. Now, the way the components are connected, the way they're exchanging information, as Michael Nygaard says, it defines the components' degrees of freedom. How freely these components can change, or how we can connect them without being afraid to break something in other parts of the system. So when designing coupling, we want to try to allow only the changes that we need in the system. For example, we can try to anticipate future business requirements or changes in business requirements and try to make them possible. Try to support them with our design, how the components are coupled. Usually in a way of encapsulating the affected areas in one component and trying to prevent cascading changes from happening, because that's where, when you change one place in the system and suddenly something unrelated breaks, that's where the fun begins. So that's a design decision, how we're connecting these components, and it has the direct effect on how we will be able to evolve that system in the future. Now, to understand how coupling really affects our day-to-day work, let's see 3 dimensions of coupling. Dimensions of strength, distance, and volatility. Now, I have to warn you, strength is going to be the heavy one. We're going to spend the most of our time here. Now, don't try to remember everything. We're going to do some history lessons. We'll walk through the history of software engineering and how coupling was evaluated in the past, or in other words, things that we have forgotten by now. But then we'll combine that into a different framework, and I'll tell you that now it's time to start to remember stuff, okay? So strength. Strength is the most obvious effect of coupling. It's like a gravitational force that pulls components together, meaning that if the strength of a connection is high, then the probability of cascading change between these components is high as well. Now, as our industry evolved, a number of models were introduced to evaluate the strength of a connection, namely coupling in structured design and a model called Khononov. Who here is familiar with structured design? 3 hands, that's a record, absolute record. Khononov? That's another record, 4 hands, 5. Cool. For the rest of you, let's briefly go over these models. So first, these models are really old. They were defined in these books. You're not going to find them on Amazon, but if you do manage to find, especially the red one, it's interesting that if you ignore the publishing date, it's from the 70s, it sounds like the authors are speaking about the problems we're experiencing today, so nothing really changed in 50 years. Anyway, back in those days, they defined 6 levels of interconnectedness: content, common, external, control, and temp and data coupling. Now, these levels, they may sound somewhat unintuitive, and that's because they're based on terminology from languages such as COBOL and Fortran, so luckily we're not familiar with that, so let's see what they mean. First one is content coupling. And here we have 2 components, and one of them directly references the implementation details of another one. In other words, somebody is using private interfaces, something that was not intended for integration in order to communicate with another module. Back in those days, the classical example would be a go-to statement, where you know exactly what happens on line number something in another module, and if that changes, then your code won't work anymore. Luckily, we're not doing such death-defying stunts anymore, but we have our ways. For example, if we are using reflection to read the value of a private field or call a private method, that's content coupling. Common coupled modules communicate through a globally accessible shared memory space. That shared memory space is just a collection of bytes without any structure. That shared memory space does not enforce any integration contract or schema how the data should be formatted. So the two connected modules have to duplicate that knowledge, and of course, if one of the authors of one of the modules decides to change that structure, the authors of the other modules, they are going to be surprised by that. They have to communicate that, and since this integration method is not properly documented, it's not properly enforced, it's quite implicit and it's fragile. A slightly lower level of interconnectedness is external coupling. It's the same shared memory space, but now we have a variable or an array of variables. So at least we have some format for data exchange. Now, if we link it to our reality, then common coupling would be, for example, working with two components reading and writing data to a file in S3, binary file. So they have to duplicate that knowledge, how the data is formatted. And external coupling would be two components using the same database. They are modifying the same data in the same database. At least that database is somehow helps to enforce that integration contract between them. Control coupling happens when modules do not encapsulate their business logic properly, meaning that business functionality is not encapsulated in one module, but instead it is, in some sense, it is spread between two connected modules. And one of them is dictating to the second module how to do its job. In essence, the second module is not independent. It cannot do its job properly because some of its business logic that should have been there resides in another module that controls it. Stem couple modules, they're communicating by exchanging data records. Now, these data records are data structures that provide a bit more information than is really needed for integration. Say I'm talking to a CRM system and I'm asking for an email of a customer. Instead of an email, I'm getting dozens or hundreds of fields. An email is going to be there. I can find it. But sharing that extraneous information makes the consumers more prone to changes in the upstream's data structure. If they suddenly decide to change something in those data structures, I have that knowledge. So I'm going to be affected by that change as well. And finally, data coupling. Here we have two modules communicating through exchanging arguments, primitive types. In other words, they are minimizing the amount of information that is shared across their boundaries, and that information is properly documented. So this is the most desirable level of coupling in structured design. Now let's see the next model called connaissance. This one was introduced in 90s, about 20-30 years later, and it was supposed to provide a more fine-grained way of evaluating coupling in object-oriented code. That word connaissance, it means having been born together. And according to the author of this model, two components are connaissant if a change in one component requires a change in another one. Or if you can postulate a reasonable change that's going to require both components to change. Now, it has to be reasonable. Like, if you have a module that implements a CRM system, changing it to a printer driver is not a reasonable change. It should be something that is reasonable from the business perspective. So, to evaluate coupling, Miller Page Jones proposed 9 levels of interconnectedness, and he divided them into 2 types: static connaissance and dynamic connaissance. Static is compile time dependencies, things you can identify by reading the code, and dynamic connaissance is all about runtime behavior, things that you can analyze by examining how things relate during the runtime of the system. Let's start with static connaissance. The lowest and the most desirable level here is connaissance of name. Here we have two variables that just have to have the same name in order to reference the same thing. If you're reading a value from a variable, you need to know its name. That's connaissance of name. That's the lowest level. If the name changes, you will have to change your reference as well, but that's the minimum amount of knowledge that is being shared according to this model. Now, slightly higher is connaissance of type. Now, usually these two, name and type, they come together because this one means that you need to know the type of that variable. So, if you need to know whether that variable is a string or an integer, you have connaissance of type, but that's also considered almost the lowest level in this model. Slightly higher is connaissance of meaning. And the best example here is that status equals 7, that magic number. Now, if two modules communicate by exchanging these magic numbers, both of them have to agree on the meaning of these numbers, of their values. So they're duplicating that knowledge, what these numbers means, and of course, if there is a change, both of them have to change together, and it's a bit less explicit than the previous two types. Connaissance of algorithm happens when two modules have to agree on the use of a specific algorithm in order to understand each other. For example, let's say we have two services communicating by exchanging encrypted data. They better agree on an encryption algorithm, because if they're using different algorithms for encrypting and decrypting data, something is not going to work. So that's connaissance of algorithm. Now, there is a very common misconception that drives me nuts, to be honest, about this level, is that many people say that it's about sharing the algorithm, the implementation of the algorithm. Or in other words, sharing business logic into components. That's not the case. Duplicating business logic would take us way higher on that scale than level 4 out of 9. So this is not about duplicating business logic. It's just about two modules having to agree on the use of some algorithm to understand each other. That's it. Finally, we have connaissance of position. And here, two components are communicating by exchanging arrays of values, where the meaning of each value is dictated by its position in that array. Well, it's really rare nowadays. The closest example I can think of is, let's say we have send email method that accepts 4 strings from to subject body. So 4 types are equally the same, and whoever calls that method has to make sure that they're putting the values in the correct order, because that signature makes it easy to make a mistake and misplace them and cause incorrect behavior of the system. So that's connaissance of position, and that's the highest on this static connaissance scale. Now let's see runtime dependencies, dynamic connaissance. And here the lowest level is execution. This one means that we have operations that have to be executed in a specific order, one after another, or otherwise the system is going to be in an incorrect state. For example, let's say we are working with a database. First we have to open a connection, then we begin transaction, then we execute a query, commit transaction, or roll it back, close the connection. That's the order. If we close the connection and then open it, it's probably not going to work as we intended, because the connection is not going to be properly closed at the end. So that makes these operations connaissant by execution. A closely related level is connaissance of timing. And here we have a time-based dependency between multiple behaviors. Going back to the example of database, let's say we open a connection and nothing happens for 30 seconds, we have to time it out. So we had that time-based dependency, the time that has to pass between opening a connection and timing it out. So that's the idea of connaissance of timing. We have time-based dependency between multiple behaviors of a system. Connaissance of value happens when values have to change together, meaning that there is a business rule or invariant or business algorithm that says that multiple values have to change together as an atomic transaction, because otherwise the system is going to be in an incorrect state. For example, let's say we have this data structure that represents 3 edges of a triangle. If we're changing one of the values, in order for a triangle to remain mathematically valid, we have to change the other 2 values as well. So that makes these values of this data structure connected by value. And finally, the highest level on this scale is connaissance of identity. This one means that 2 objects must reference the same thing, the same instance of another object, in order to work correctly. For example, let's say we have 2 components, 2 modules working on the same set of data, reading and writing the same set of data. So they probably have to work with the same database so that they can see each other's changes. If they're not, if each is going to have its own database and the data is not synchronized in any way, then the system is going to be in an incorrect state. So that's the highest level of connaissance of identity. Now, these 2 models, structure designs, coupling, and connaissance, there are some similarities between them. However, they are quite different. They're reflecting different aspects of design. Some things are reflected better in structure design, others are reflected better in connaissance. And moreover, both have some blind spots. For example, let's say that I'm writing C# or Java code, and I'm reading the value of private field through reflection. Where does that put me on the structure design scale? What do you think? Come on, people, let's wake up. I know the coffee break is after my talk, but still. Yes, exactly. Content coupling, the highest one. I'm using private variable. It was not intended for me. The highest one. In other words, my code sucks. What about connaissance? What do I need to know to read the value of a private field? Name, awesome. So one says my code sucks, the second says that my code is awesome, and of course I'm going to listen to connaissance. Just kidding. Okay, so there are some blind spots in both models. So since structure design they started working on it in the late 60s, connaissance in 90s, we have this cadence of 30 years to start thinking about a different model for evaluating coupling. So I want to show you a model that I call integration strength. I used it for quite some time now, and for me it worked really well. So I want to share it with you, and the goal here is to remix the previous 2 models into a more coherent tool that we can use in additional situations that will give more precise results. That it has to be practical. It should be easy to use without having to learn what external and common keywords mean in Fortran. Yeah, so that's integration strength. And it has only 4 basic levels: intrusive, functional, model, and contract coupling. By the way, I told you that I will let you know when it's time to start remembering things. Now's the time. So let's see them. Intrusive coupling, it's the synonym for content coupling in structure design. We are using something that was not intended for integration. We're using private interfaces, we're using implementation details, and of course, such integration method is fragile and implicit. The authors of that upstream component may not even be aware of that integration taking place. So any change they are going to make to the implementation details It has the potential to break the integration and cause cascading changes to the consumers. So in a sense, with this level of coupling, we have to assume as if all knowledge about the implementation details is shared across the boundary of the upstream. Functional coupling means that two components implement closely related functionalities, business functionalities. Its practical implication is that the same change in business requirements is very likely to trigger cascading simultaneous changes in the two components. They will have to change together. An extreme example here would be two components duplicating the same business rule or the same business algorithm. If that algorithm changes, they have to change together. And to make this even more implicit, they don't really have to be connected. They can be completely independent components of a system, no physical connection between them, but still they have to change together. So that's quite high on this scale. And also, less extreme examples would be all cases of dynamic connaissance. Connaissance of execution, timing, value, identity, all of them reflect these functional dependencies. Next one is model coupling. Did people hear? Oh, okay. So for you, bounded context, model is shared inside the boundary. That's model coupling. For the rest of you, first of all, read about domain-driven design. You won't regret it. So when we are implementing business logic, we are actually building a model of a business domain. We are not copying it as it is in the code, but we have to come up with a model that's going to reflect some of the aspects of the business domain that will allow us to solve the problems that the system is supposed to solve. So this model can be shared between multiple components of a system. When that happens, they're model coupled by sharing the same model. The practical implication here is that we do want to evolve that model over time because we learn more things about the business, we gain more insights into the business, and that allows us to improve the model. However, if it's being shared between multiple components of a system, it makes it really hard to evolve it over time. Because, again, it causes some cascading changes, and sometimes we tend to be lazy and try to say, okay, this model is good enough, it works, let's leave it like that. Okay, the lowest level is a contract coupling. And here we have an explicit integration contract that is being used by two connected modules. The idea is that integration contract is decoupled as much as possible from the implementation model, from that model from the previous level. Meaning that with this level, we aim to contain as much changes to the implementation details of the upstream component as possible. As long as that, let's say, new model that's being evolved in the upstream can still be translated into the same integration contract, well, it's not going to affect our consumers. They're not going to be aware of it. So in a sense, here we're minimizing the amount of knowledge that we are sharing across the boundaries of the upstream component. We are minimizing the knowledge that we are sharing, and thus we are minimizing the chances for cascading changes happening across the system. Now, one thing that I have of course forgotten is model coupling. All the static connaissance levels, they are relevant here in this boundary of model coupling. Okay, let's go on. So again, going from intrusive, where we share the most knowledge, all the way down to contract, where we minimize the knowledge that's being shared. On the top, we have implicit integration interfaces. As we go down, we get explicit integration interfaces. Now, let's say that we have this intrusive coupling between two components of a system. We designed it intentionally. My question to you, is this necessarily a bad design? Who thinks it is? Who thinks it's not? Who thinks it depends? Consultants. Yeah. Yeah. To answer that question, we have to talk about other dimensions. And the next one is distance. And turns out the physical location of components of a system in the code base, it also affects our coupling. Coupling can happen between individual statements, methods, classes, namespaces, components, services, microservices, whole systems, whatever. And the larger the distance between two connected components, the higher the coordination that is needed to implement a change that affects these two components. So let's say we have to modify two methods in the same class. In that case, the coordination effort that we will need is going to be way, way lower than in a case of, for example, implementing a simultaneous change in two microservices. So in other words, the cost of making a change in a system, a change that affects multiple connected components, is proportional to the distance between them, between these components. Now, another way to look at this notion of distance is what we usually call levels of abstraction. The higher the level of abstraction, the higher the distance. Now, there is another line here, and that's life cycle coupling. It's inversely proportional to distance. And here, the closer components are located to each other, the higher their life cycle coupling, meaning that they have to be developed, tested, deployed simultaneously. So if you are modifying, let's say, let's go to the left side, a statement in a method, well, chances are that it's going to inadvertently affect other statements in the same method. But as we go further to the right, that life cycle coupling is being reduced. Now, the interesting thing about distance is that it's not only about the design. It's also by the organizational structure. Because if we go back to the first line, the red one of coordination, let's say we have two microservices implemented by one team versus two microservices implemented by two teams. In the latter case, the coordination overhead is going to be way higher. And thus, we're dealing with higher distance between them. So again, the farther the distance, the lower the chances of inadvertent changes because of life cycle coupling. However, the higher the coordination overhead if we do need to implement a change that affects two connected components. Now, another question to you. Let's say we have two systems, meaning that the distance is huge, and functional coupling between them, meaning that they are implementing closely related business functionalities. Same question, is it good or bad? Who thinks that it's good? Who thinks it's bad? Consultants? Yes. Let's see the third dimension. So the question another question that we can ask here is, if a tree falls in a forest and nobody's around to hear it fall, does it make a sound? Same as here. Let's say we have two strongly connected components over a huge distance, but the upstream never changes. Who cares about this coupling? How it's going to affect us if there are going to be no changes in the future? So let's talk about the dimension of time, or volatility. And the question here is, how often do the coupled components actually change? And of course, it's hard to predict the future, but we can use some tools, some frameworks to analyze the functionalities that we are implementing and deduce what should we expect from the future. And now I'm going to wear my domain-driven design hat and show you the notion of domain-driven design's subdomains and how it can help us here to predict the future. So in domain-driven design, the main concept is business domain, for which we are building the software, but it can be decomposed into a coherent set of use cases, interrelated use cases that are closely related from the functionality perspective, and they are called subdomains. Different subdomains are needed for the company to succeed in its business domain, but not all of them have the same strategic importance. Actually, we have three types: core, generic, and supporting. Core subdomain is all about the company's competitive advantage. This is how the company is making money. Here we're implementing some know-how solutions, some new algorithms, inventions, smart optimizations, things that our competitors don't have, things that give us an edge over our competitors. On the opposite, generic subdomains are solved problems. Here we have to implement some functionality, but we have an existing solution that we can just use, like an off-the-shelf product or open source solution. And we can use it, and our competitors can use it, so there is no business differentiation here. So again, compared to the first one, here we have no competitive advantage. Everybody is using the same solution. And finally, supporting subdomain is somewhere in between. This is something that we have to implement ourselves, but we would be happy for a supporting subdomain to be generic, because we're doing it just because we have to support some functionality of a core subdomain, but it doesn't provide any competitive advantage. So usually supporting subdomains are simple things like CRUD data entry screens, ETL jobs, etc. Things that are simple, that they do not provide any competitive advantage. We don't really care if our competitors are going to copy it. So comparing the three subdomains means that core subdomain is the most volatile one. If we are implementing a module that it belongs to a core subdomain, it's going to be volatile. Business is interested in changing it as often as possible, both because in many cases the business early on is not aware of how to implement that functionality, and also because over time the company needs to catch up with its competitors and stay ahead. So they extend the functionality of core subdomains. So these are the three dimensions of coupling. We have strength, distance, and volatility. Now, interesting things can happen if we combine them together. So let's see how we can balance them in order to achieve modular design. So first, strength and volatility. If we have high strength with high volatility, we have high maintenance effort, because things are going to change often, and every time they're changing, we have high probability of causing cascading changes. So high maintenance effort. Strength and distance. When both are high, we have high cost of evolving the system, because any change that is going to be quite frequent because of high strength is going to be costly to implement because of the high distance. And finally, distance and volatility. High volatility over high distance means that we have very high coordination or communication effort to evolve that system. It's going to change frequently, but the high distance requires us to communicate over distant teams, for example. Now, the most interesting thing is going to happen if we're going to combine the three of them. And that allows us to evaluate the maintenance pain. So let's say you have two components that are referencing each other. You know the integration strength, the distance, and the volatility. These values will allow you to evaluate how much pain you're about to endure in your future. And to evaluate the pain, all we have to do is to multiply their values. Meaning that if the three, all of them are high, guess what? Your pain is going to be high as well. However, if one of them is 0, your pain is going to be 0 as well. Let's quickly go through some examples. First, let's say that we have low strength, 0, over high distance with high volatility. Yeah, it's going to be making cascading changes is going to be expensive because of high distance. High volatility makes it even worse. However, low integration strength balances the previous two out and minimizes the chances of those cascading changes happening. So our pain is 0. Now the opposite. Let's say we have high integration strength and high volatility, but the distance is 0, meaning that we have very high probability of cascading changes and that business domain is going to evolve frequently, but that minimal distance reduces the cost of implementing those cascading changes. So again, it balanced out. In other words, this relationship represents what we usually call high cohesion. We have related parts located close to each other in the same place. So that whenever we have to implement that cascading change, it's going to optimize or reduce our cognitive load. We know exactly where to look for things we have to modify. And finally, high strength over high distance may be reasonable if the upstream component is not volatile. For example, let's say that you are working with a legacy system and it's on life support. It's not going to be changed. In that sense, you can go ahead and use its implementation details, like access its database directly to read some records. That schema is not going to change in the future. So that's somewhat pragmatic dimension of coupling. If things are not going to change, sometimes you can round some corners. Now, the whole algorithm is, when talking about integration strength, of course, we want to minimize it as much as possible. We want to eliminate accidental coupling, accidental knowledge that is being shared across components' boundaries. Not always it is possible to go to the lowest one. Sometimes you will have components that share the same functional requirements, so they are going to be functionally coupled. There is no way around it. Also, sometimes you need to use the same model of the business domain, so that's model coupling. There is no way around it. There is no point in trying to jump through hoops and minimize it to contract coupling. So minimize the strength as much as you can. And if you end up with strength and distance, with strength and volatility both being high, then you can reduce the distance to balance that high strength and high volatility. Let's see how much time do we have. You know what? I don't care. I have those technical issues, so I'm giving myself extra 5 minutes. So a quick example of integration strength. We usually say that working with another microservices database directly is a big no-no. You should never do it. Let's use that example of working with another components database and see where it can put us in the integration strength scale. So first, if the component B is not aware of that integration taking place, that the component A is going there to read those values, that's private interface, and that's intrusive coupling. Next, let's say that they did have this conversation, and they decided they're going to share the same database because they have to. That makes them functional coupled, meaning that it is a design decision. It's not component A breaking the rules like in the first case. Now, let's say that we have a BI department, just as they love to do, fetch some data from the operational database to analyze it. What they're doing, they're model coupling themselves. They are duplicating that model, and when it will have to change, they will have to change simultaneously, both in the operational system and in the BI analytical database. And finally, sometimes we can use a database for integration. We can put integration-specific data there. For example, like in the data mesh approach. In that case, yes, we are sharing the database, but it's still integration contract, so it's contract coupling. Microservices, in many cases, I've heard about companies taking a monolith, extracting some functionality into microservices, and everything was awesome. So okay, let's go and proceed and decompose the whole monolith, and then suddenly they end up with a distributed monolith. They hate it. They go to write blogs that microservices suck. And what that usually means is that they use some ineffective strategy for decomposing, for extracting microservices out of a monolith. For example, something weird like saying that a microservice shouldn't be longer than 20 lines of code. And by doing that, that's a very good way to introduce functional coupling. Integration strength is high. Distance is high as well because we're talking about microservices. But when they started with that little POC, usually what's going to be the first component they're going to try to extract? Usually it's not going to be some business critical functionality. Or in other words, it's going to be a supporting or a generic subdomain. So the volatility is 0. And then they proceeded with the same decomposition logic, but for their core subdomain functionalities, and they ended up with the 3 of them being high. High strength, high distance, high volatility, high pain. Okay, I'm going to skip the domain-driven design examples because this is not a domain-driven design conference and I'm already late. So, to wrap it up, coupling, it's an inherent part of system design, just like drawing boxes. Think about the lines, connecting them. Think about how much knowledge you share between the boundaries of those boxes, how much knowledge flows through those connections. You can roughly categorize the knowledge into 4 types: intrusive, functional, model, and contract. We have different distances that affect the cost of implementing cascading changes and the chances of inadvertent cascading changes because of lifecycle coupling. And finally, volatility, the pragmatic dimension that allows us to evaluate how much a problem, high strength over high distance, is going to be in the future. And yeah, that's the pain function. If you multiply the 3 of them, you will get the maintenance pain you're going to endure in your future. I really hope that the day when that book is going to be published is close. I cannot promise anything at this point of time, but in this book you will find all this information and a bit more about the integration strength, and also about that pain function is going to be evolved a bit to reflect some other important design aspects, such as complexity. And with that, I don't know if you have time for questions. Should we do it? Yes?